Welcome back to the next chapter. Chapter 11 is on statistics and probability. This is going to start out very similar to stuff you've already done. In fact, a lot of the beginning of this chapter you probably already know. By the end of the chapter, we will be doing new stuff. This first section might be new, might be reviewed, depending on what you've seen in the past. We have a couple equations in here, but the section's on permutations and combinations. So, before we get to our learning targets, I have a question for you. The question is, what is this? Alright, it's a lock, yes. What kind of lock? Yeah, it's a master lock. Not looking at the brand. What else would you call this lock? Are you thinking it's a combination lock? That's usually the name that people give us. That's probably what you're thinking. It's combination lock. In fact, when I found this picture, I looked up combination lock and boom, it came up. It was the first picture that came up. Anyway, we'll come back to this later. Our learning targets for today. I can solve problems involving the fundamental counting principle. Yes, you read that right. We're going to be counting today. And I can solve problems involving permutations and combinations, which should make sense being that the title of the section is Permutations and Combinations. So, let's start out with the fundamental counting principle. So, we are going to be counting the number of ways things can be done. For instance, let's say I got dressed this morning. It's a safe assumption. I, in fact, did get dressed this morning. And I'm going to simplify this just a little bit. We don't need to go into everything I put on. But let's say that I had 5 pairs of pants to choose from. I had 6 pairs of socks to choose from. And I had 2 shirts to choose from. Now, I put on other stuff. For instance, I wear a ring. So, but I have these. And how many ways could I have gotten dressed? All right, the pairs of pants, well, that's actually one thing for each of those. The pairs of socks, I can't mix and match my socks. I can't do it. The seams are in the different places. It does not happen. So it's just 6 pairs of socks. And let's also assume that I got dressed in the dark, which is a fairly safe assumption, and that I might be mismatched and none of this stuff goes together. So how many ways could I have gotten dressed? Well, we can count. We have 5 pairs of pants. So I could have picked any one of those 5 pairs of pants. And then from each of those choices, I had a choice of picking 6 different pairs of socks. And you can see this is already getting really confusing down here. And then from each of those, I could have picked 2 shirts. And so we just have to count all the end of those little lines here, which I wouldn't try because there's a lot of them that are just overlapping. If I really wanted to do it this way, I would have had to use a much bigger area and be a lot more organized in my things so they weren't all overlapping. But this is silly, especially because this is actually a fairly small type of problem. 5, 6, and 2 for our options. That's not a lot. Most of the times it'll be bigger. We don't want to have to make a diagram like this. And so that brings us to the fundamental counting principle. How can we count the number of ways without actually physically counting the number of ways? Well, the fundamental counting principle says if there are A ways of choosing the first thing and B ways of choosing the second thing, then there are A times B ways to choose both things. And the nice thing about this is it expands to 3, 4, 5, 6, however many things you need to do perfectly. You just multiply them all together. So here this says if I just want to choose pants and socks, I have 5 times 6 ways of choosing my pants and socks. So we have 5, and then each of those has 6. Doesn't that just make 5 times 6 would be 30? And then so 5, 6, and then times that 2, we just have 5 times 6 times 2 is 60 ways for me to get dressed in the morning. So there we go. And that's really all the fundamental counting principle is. This times this times this. Sometimes our our categories will depend on the others, and we'll see an example of that in just a second. But first, try a problem. So, let's say you're getting school lunch. Take your life in your own hands, and you can select one item from each type. So there's 3 main courses. So for lunch we have pizza, we have Spartan burger, not entirely sure what that is, and we have chicken strips. And there's 4 sides. You could get a salad, you could get fries, you could get beans, or you could get coleslaw, 2 desserts, ice cream, or pie, and 5 drinks. You could get chocolate milk, regular milk, water, orange juice, or apple juice. How many ways could you choose to get your lunch? So, go ahead and pause this if you need to. You may already have an answer because these questions aren't all that tough. But pause it, get your answer, and then come on back. Do you have it? Did you even need to pause it? So this, just like what we did here, we had 5 times 6 times 2. It's just 3 times 4 times 2 times 5, which is 120 ways of doing it. So you could go through the lunch 120 times and get a different combination each time. And that's all the fundamental counting principle really is. But as I said, sometimes the things will rely on each other. A great problem for this is license plate problems. And we'll get a few of these because they're really easy to make and you can change them up a little bit pretty quickly. So, for the sake of our problems, let's say our license plates are 3 letters, then a dash, and then 3 numbers. So how many ways could we make license plates? So, what I like doing is I like getting each of the spaces out. And then we can figure out how many ways can we pick for this space. So this is going to be a letter. How many ways can we pick a letter? Well, there are 26 letters in the alphabet, so we have 26 to choose from. And then, how could we pick the second one? Well, there's still 26 letters, so we have 26 to choose from. And then the third one, 26. And we're just going to multiply these together. But we also have to have our numbers. It's a single digit. How many ways can we pick a single digit? No, it's not 9. It's 10. Because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. So there are 10 ways of picking the single digit for each of these spots. And then we just need to multiply all of these together. 26 times 26 times 26 times 10 times 10 times 10. I would recommend using a calculator for this problem. Just because. And when you do, you get the license plates. That would be 17,576,000 license plates, which is why I would recommend a calculator. And now I mentioned that these are really easy to switch up. So let's say we can't repeat any digits. So we still have our 6 places. How many options do we have for that first letter? Still 26. Now how many do we have for the second letter? It's not 26 anymore because we can't repeat whatever this was. So we now have 25 options. And then for this one, we have 24 options. Then for our numbers, we still start out with 10, and then 9, and then 8. When we multiply these guys together, we're going to get 11,232,000 license plates, which, notice we just dropped a little over 6 million by not allowing repeats. That's a big deal if you need a lot of license plates. Another option we could have, instead of no repeats, is let's just say that it can't be next to itself. So we can't have like a double letter. We can't have AA. Well, how could we do that? We still have our 6 spaces. How many options do we have for the first one? Still 26. And then the second one? Well, it can't be that one. So that means 25. And then the third one, it can't be that one. It could be this one. It just can't be right next to it. So it just can't be whatever this is. So we still have 25 options there. And then the numbers will do about the same. 10, and then anyone but that one, and then anyone but this one, would be, again, 9 options. Multiply them together, and we get 13,162, or 13,162,500 different possible license plate combinations. So we gained almost another 2 million back there. And so these are just ideas of the fundamental counting principle. And this will get you through a lot of this type of problem. We're going to look at permutations and combinations, which will get us shortcuts that will work in certain situations. But as we look at the permutations, we'll see that it's just this that we're doing. And this isn't all that hard. And what's funny is when people do, well, I would say when people do struggle about this, it's not when people struggle. It's when your parents come up and it's like, oh, what are you watching your video on this today? You're like, oh, I'm learning how to count. And then just look at their face, see what they say. So our next thing that we're going to look at is a topic that I get kind of excited about it. It's factorials, and factorials are fun. And because, we have numbers, we have letters, we even have words with log and stuff. Well, now we get to use punctuation, like the exclamation point. We can use the exclamation point in math. How much fun is that? So, an example of a factorial would be something like 7 factorial. That's actually how it's pronounced. 7 factorial. A fun game to play in English is when you have to read aloud. Whenever you come to an exclamation point, you just pronounce it factorial. So, in Romeo and Juliet, die Mercutio factorial, and just see what your English teacher says. It's pretty fun. So now, what does this 7 factorial mean? 7 factorial is the 7. It's not just 7. It's a 7. It's excited to be here. In fact, it's so excited, it's bringing all of its friends along with it. 7 factorial equals 7 times 6 times 5 times 4 times 3 times 2 times 1. Granted, we don't really need the times 1 there because it's really not doing anything. It's like that friend that, it doesn't matter if it's there or not. It doesn't make a difference. You know who I'm talking about. That's kind of that 1. But we'll include it anyway. And so any factorial, like 13 factorial, is 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. It goes all the way down to 1, no matter where you start from. And so that's what that is. There is a factorial button in most calculators. In the graphing ones, it's in the math menu. You go over to prob for probability, and it's like number 4 down the list. You type it in exactly like this, 7 factorial. And in scientific, they have them. It's usually second something or another. I can show you where it is on your particular calculator. Anyway, so 7 factorial is this. We just multiply those together to get 5,040. And so, how can we use these? Well, a lot of times our factorials are actually going to be in fractions. So we're going to have stuff like 30 factorial divided by 27 factorial. Now, I'm going to show you how to do this by hand because it is possible for me to give you factorial that's so big that your calculator cannot do the problem, but you will be able to do it by hand pretty easily. And I'll show you how I'll do that in just a second. But we're going to do it by hand. We're going to expand this 30 factorial. So it's 30 times 29 times 28 times 27 times 26 times 25, etc. And the 27 factorial is 27 times 26 times 25, etc. But isn't 30 factorial, so that's 30 times 29 times 28 times 27, 26, 25, 24. Isn't that just 27 factorial? And this is 27 factorial. And everything is multiplied, which means we can cancel. So this problem just becomes 30 times 29 times 28, at which point I would probably use a calculator for that to get 24,360. But we didn't have to go all the way down. We didn't have to do 30 factorial, get this number that's enormous that will give us scientific notation in the calculator, divided by 27 factorial, which will also give us scientific notation in the calculator to find our answer. And what's fun is that when you divide factorials like this, they'll always come out as a whole number because we're looking at the number of ways we can do things. It'll always be a whole number. So I mentioned that I would make a problem so big that your calculator won't be able to handle it, but you will be able to do it easily. 2017 factorial divided by 2016 factorial. Try doing 2017 factorial in your calculator. Even the graphing calculators will give you an overflow error because it is too big. But if we expand this, how far do we have to go? Just that one place. It's 2017 times 2016 factorial. 2016 factorials cancel, and our answer is just 2017. It's as easy as that. Calculator can't do it because it's going to try and do all the top and divide by all the bottom, and it cannot handle that. We can think a little bit, split it up, cancel, and then we just get our answer without really doing any math at all. It's kind of fantastic. So we're going to use our factorials to help us with our permutations and combinations. So looking at permutations and combinations, these are very, very similar. They're special cases of the counting where certain stuff happens. We're going to go down like we have a certain number of things, and we're going to pick some of those things to put on there. And the difference between a permutation and combination is in permutations, the order matters. And in combinations, the order does not matter. When I got dressed, it's combination because it didn't really matter which way I put my clothes on. Same thing when you picked your lunch. It didn't matter if you picked the main course and then the dessert, or the dessert and then the main course. You're just looking at what you had on your plate at the end. So we have the order matters and order doesn't matter. Let's look at permutations first because this really goes with what we were just looking at. So in a permutation, we're going to do our problem. So I built a house a couple years ago. Well, I didn't build the house. I had other people build the house for me. If I built the house, I would probably still be working on it and it would be falling down. Anyway, I had a house built, moved into it, and I got to decorate my office downstairs. And so naturally, I decorated with swords. What else would I decorate with? Anyway, I had 11 swords that were hang-worthy, but I only had 9 spots to put them. This is a problem. But how many ways could I have hung the swords? Now, the order matters, because if you put Glamdring in one place and Narsil in the other, it changes if you switch them around. And if you understood what I just said, fantastic. Well done. You got your nerd star for the day. Anyway, how many ways could I hang these 9 swords in these 11 spots? No, sorry. 11 swords, choosing 9 of them to hang in the 9 spots. I know some of you are thinking right now, is this actually a true story? Yes, it is. Those are the ones I have hanging. Technically, this is an axe, and it's a knife, but still. Yes, those are in my office. All right, so anyway, though, we're going to do this problem. So I have 9 spots. How many ways could I pick one for the first spot? I have 11 to choose from, so 11. And then for the second spot, well, there's only 10 left to choose from because I can't hang the same sword in 2 different places. That violates the laws of space and time. And then the 9, then 8 in the next, and 7, and 6, 5, 4, and I had 3 to choose from for the last spot. And I can multiply these together to get that I had 19,958,400 ways of hanging the swords. Obviously, some like you couldn't put this one right where this is, but still. So that is how that works. But we have an equation, so we don't actually have to do this every time. And the equation, there's some notation here. We have NPR, this would be N pick R, and permutate R. it's going to equal n factorial. That's how many we're choosing from. So in our case, 11, it's the bigger of the two numbers. Then divide by, we subtract them, factorial. So in our case, it would look like 11 permutate 9, which is going to be 11 factorial over 11 minus 9 factorial. One thing about factorials, you cannot distribute those through parentheses. You have to do the subtraction, and then you factorial. 11 minus 9 is just 2. So it's 11 factorial divided by 2 factorial. Well, 11 factorial is 11 times 10 times 9 times 8 times 7 times 4 times 3 times 2 times 1. And the 2 factorial is 2 times 1, so those two cancel, giving us 11 down to 3. And so this works perfectly with that. And this, you can also do this in your calculator. It's in the same menu as a factorial, or it's in the same area on the TIs. You go to the math menu, go over to prob for probability. This and the combination equation are both right there. They're pretty easy to use, but I can show you how if you need me to. And another thing, the book uses NPR. I don't know why, but I must have learned it this way. I always use NPK, K instead of R. It just changes what the variable name is. It doesn't change anything, but if I, for some reason, say NPK at some point, it's the same as NPR. And same with combinations. So for combinations, oh, and this gives us the same thing. If we just plug this into our calculator, we get this number. Combinations. So I have this house, and my office I decorated with swords. My theater I decorated with lightsabers. If you have 9 lightsabers to hang, but only 7 places to hang them, that's a trick question. You figure out how to hang all 9 of them. But upstairs, where visitors see, I didn't get to decorate that because swords, safety for the children, things like that. So my wife decorated, but she let me pick what went on the wall. I just didn't get to pick where to put it. And she also picked the pictures I had to choose from. So I'm going to use the same numbers. We have 11 pictures, but only 9 spots to hang them. How many ways can I choose which ones are hung? Again, I don't get to put them up, but I get to pick my 9 favorites. Which ones do I want on the wall? That's a combination. The permutation is where do you put them? You actually have the control over that. And so our formula for this is very similar to the permutation one. We just have another r factorial in the denominator. So in our case, we have 11 choose, that's what the C is, 11 choose 9. And notice choose is in the question pretty much every time. 11 choose 9. It's going to be 11 factorial over 11 minus 9 factorial times that extra 9 factorial. We can simplify the 11 minus 9 to be 2 factorial. And now we can plug this into our calculator, but again, sometimes you can get numbers that are too big. So how do we do this by hand? We're going to expand the 11. Not very far, though. We're just going to expand it to the bigger of these two numbers. In this case, 9. So 11 is the factorial is 11 times 10 times 9 factorial. The 9, and then 2 factorial is just 2 times 1. 9 factorials cancel. So we just have 11 times 10 divided by 2. 10 divided by 2 is 5. 11 times 5 is 55. So I have 55 ways of picking my 9 favorite pictures out of the 11 that I had to choose from. And that's the combination. Again, this is going to be the same place as this on your calculator. In the probability, there will be a lot of times where calculators will be helpful, but also a lot of times where we don't need them. Like this, we didn't need a calculator to do this, as long as we were smart about what we did. So it's permutations, combinations. One last question. What is this? I know I asked that earlier. We said it's combination lock. But Can you put your numbers in any way you want? No. Anyone who's forgotten their code knows that it matters what order you put those numbers in. So this isn't a combination lock. What should it really be called? It should be a permutation lock. And it is one of the most misnamed things out there. A number of years ago, some of my students after this started a Facebook page on changing the petition to change the name to a permutation lock. I don't think it went anywhere, but I think it's still there. Anyway, don't forget to post a comment. Should have lots to comment on this one. And I will see you in class.